Hello everyone, I'm Alessandra Ceci, a PhD student in Industrial Engineering at the University of Rome Tor Vergata. The title of my work is Mechanical Characterization of TPMS Cellular Structure produced using the lost PLA method. Today, I will begin with a brief introduction explaining why this topic was chosen, what the cellular structure are, and where are used. Cellular solid, characterized by a network of open or closed cell, like a foam or lattices, are used to reduce the weight without compromising the mechanical and structural performance. Nowadays, there is an increasing demand of the weight components in the sector with the weight-saving energy absorption are critical. Additive manufacturing help to realize, to produce this type of structure with a complex shape. There are various applications, for example, in automotive, like lightweight components and crash absorption, in aerospace for structural efficiency and weight reduction, in biomedical for implants, and in energy and in industry like heat exchanger and structural support. The aim of this work is to design a parametric cellular cell base cell, and then realize two different types of structure in aluminum alloy using the lost PLA process. Then we analyzed the fidelity of the process and with the comparison with the theoretical weight and real weight, and analyze the mechanical behavior with a compression test to evaluate the specific energy absorption. Now let's move on to the process used for create the metal structure. The lost PLA method is similar to the lost wax casting technique, an ancient metal casting process used for create an object with a complex shape. In this slide, we can see the various steps of the process. The first step is a CAD modeling. The base cell is a parametric, so by changing the value of the parameters A and B, we can obtain different geometry, different configuration, like this. In particular, this base cell is a TPMS cell, which are smooth, continuous geometry with a height surface to volume ratio, ideal for the lightweight and energy absorption application. These are the two structure, the two CAD modeling structure with useful for the casting process. After that, we have a slicing phase. During this phase, all the 3D printing parameters are setting, and then we have a 3D printing phase. And this is the PLA model. After that, we act to the structure a plastic tube for create a venting channel, and everything we're putting in a steel container and covered with a mixture of water and plaster. Additionally, we place on the structure the weight for keep the structure in position and for create a puring channel. The mixture of water and plaster left to dry for 24 hours, and then the weight was removed. The steel container was placed in a cold muffler furnace and heated to 900 degrees C. PLA burn out around 250 degrees C, and when it completely burn out, it leaves in the plaster the negative of the structure. When the muffle furnace arrived to 900 degrees C, in electrical furnace, aluminum alloy was melted. This high temperature was chosen to prevent the metals to solidify too quickly in the plaster, because the casting is done at room temperature. After the structure was quenching and cleaning by the plaster, and this is the final result, the final structure. Now analyze the fidelity of the process. This micrograph image show the PLA and aluminum alloy structure for each configuration. By this image, we can see the good repeatability of the process. In fact, the original structure was replicated after casting without significant microscopic defects. The parameters in the table confirm this result. In fact, the deviation of the weight is less 2%. Now we analyze the mechanical behavior with the compression test. We have three different spacemen for each configuration. These are steps of the test of the compression test for the structure one, and this is the structure after the test. In the load strain diagram, we can see the typical mechanical behavior of the cellular structure. The initial phase, elastic region, a plateau with load fluctuation due to the progressive collapse of the cell, and the final densification. In the table, we can see the main mechanical parameters, and by this value, we can see the good repeatability of the process of the test. Also for the structure 2, the different step of the compression test and the final structure after test. Also in this case, we have a typical mechanical behavior of the cellular structure without load fluctuation during the plateau phase. We have a elastic region, plateau, and densification, but the specimen 2 hasn't a plateau. In fact, the load increases gradually with the deformation. And also in this case, the value in the table confirm this, the good repeatability of the test. Now let's move on to result, in particular to evaluate the specific energy absorption. These are the stress strain diagram of the test previously shown. And for calculation of the specific energy absorption, we have considered like area for the value of the stress, the area of the base of the cylinder without considering porosity. These are the value of the specific energy absorption at the 16% of deformation. And in conclusion, this work demonstrates a good fidelity of the loss PLA process with deviation between theoretical and real weight less 2%. This process is not only occurred, but is cheap and sustainable. For the effect of the porosity, we have two different behavior. The structure one with a lower density, relative density, have a progressive collapse and plateau with a low instability. Structure 2, denser, have a more uniform mechanical response and less pronounced plateau with a gradual load increase. For the energy absorption, also the behavior is different. This behavior demonstrate how small variation of the geometry have a big different value of the specific energy absorption. In the end, the application is different. For example, the structure one can be used for a protective system, biomedical implants, and vibration damping. Structure two for impact protection and structural reinforcement. That's all. Thanks for your attention.